Okay, in this example, we are going to do these single elements of bar on Ansys APDL, Mechanical APDL. Now, the problem is that the unknown parameters are the nodal displacements, the reaction forces, and the elementary stresses. In this case, we only have one single stress. Now the force is applied at rule number 2. That one is 1500 Newton, and only the diameter is given for us. So this circular cross section is provided. So in that case, the area will be 7,850 millimeters square. So those solution is the solution that I analytically calculate by hand. So it looks like this one. And after performing the analysis on Mechanical APDL, we will come and check it. Now let me directly go to the Ansys. Open Ansys icon. Here the mechanical the Ansys Mechanical interface look like this one. We do have here preferences, then after preprocessor, solution, and the general post-processor, and so on. Now let me go to the preferences, and when we click this one, this pop-up box will come. So on that one, we have to check this structure because the problem that we are going to analyze is the structure, because bar is one of the structural components. And click that one and take OK. Then let me come to the preprocessors. Here we do have element type. Click that one. Then after, check the add edit and delete element. Then add element and form element. Now we're going to use link for bar element. Then after CD finite 180 selected. Then OK. Then cancel this pop-up box, dialog box. Then after from the preprocessor we finished the setup, and minimize this preprocessor. Then go to here. I think from the element type we finished. Now let me go to the material properties. From material property, let me go to material models. Then from material models we have favorites and structural. Click this one. Then linear, from linear elastic, from elastic isotropic. Here we do have this one is the Young's modulus, and this one the Poisson ratio. Now let me go to the problem. Okay, from the problem here, the Young's modulus is 2.1 times 10 raised to 5 Newton per millimeter square, and the Poisson ratio is 0.3. Then let me fill that one into the to this box. So this one is 2.1 e to the power of 5, and the Poisson ratio is 0.3. And take this one. Okay. Then after, close this one, go back to the Ansys interface area. Now we finished for the material model. Okay, then minimize this one, go to section, from section go to link, from link we go to add. So this is number 1, or this link number 1. And after OK, then OK, the cross sections of the link is, let me say section name is A1. That one is, the area is from the problem, the area is 7850. Go to add 1. Okay, this one is A1. It is 7850. Okay, take this one as okay. Finish that one. Then after, because you only have one single element, so we provide a section for that element. Then we go to modeling. From modeling create. From create, then we come to the nodes. Then inactive coding system. So this is node number 1. Okay. The value is 0 because that point is 0. So if you leave this one as it is, so it takes as 0 point, then apply, because this one's node number 1. Okay. Then apply. Node number 2 is from the problem. Here we'll have what? The length is 300 millimeter. Go back. This one is 0. For 1, apply. For 2, it is 300 millimeter. Then okay, because we only have 2 node numbers, so finish this one as taking okay. And after we finished for the nodes, we created the node number 1 and node number 2. Then we minimize this one, go to element, from element attributes. Okay, now we have material number, material that we provided is 1. Okay, then the section that we provided is A1. Okay, take this one as this. Okay, then after go to auto numbered, then through nodes. Now I'm going to draw the bar link from this point up to the second node. Then click this one, and after click the second point, then take as okay. Now the link is created. Now we finished for the element creation. Now the next step is to go to loss, because we finished for the sections. Then modeling. Now let me go to loss. Then from loss, define load. Then apply, structural. Then displacement. From displacement on nodes. Okay, you have to select on nodes. Okay, after apply, here the boundary condition that the displacement is 0. So click this point. And after OK, the pop-up dialog box will come. Then we make all degrees of freedom should be 0. So enter 0. Then OK. Now here the boundary condition, the fixed boundary condition is applied on our geometry. Then minimize the displacement. Then after go to force and the moment, because we're going to apply the force. So the force is applied on nodes. The node is here. When we come to the problem, the force is applied at node 2. The magnitude is 1500. So here it is. Select this one. Then OK. Then f of x, because this is along x-axis. The magnitude is 1500. Okay, and click OK. Minimize force. Now we finished for the load. Then minimize this one. Go to solution. From solution, go to solve. From solve, go to current LS. That means current linear static analysis. Then OK. And after here, the solution is done. Okay, close this one, close also this one. But if you need to save this result, so go to file, then after save as, so you have to save the result as giving some names. And after saving it, now in our case, let me cancel it. Cancel. Then minimize the solution. Then go to general post processor and go there. Then after here, from those result showing icons, that we select the example, that we select result here. Okay, from that one choose this stress, then stress along x-axis, then cancel this one. Now let me go to the plot results. Okay, go there. Then first of all, let me go to the, because this one is in the 9 kinds of expression. Now let me go to the plot controls. Then after style, from style, size and shape. At this point we provide the cross sections of the bar. Okay, here, okay, check this one, check this box as it is on, and okay, so this is the face. Now when we click this isometric view, so it looks like this box. Okay, so this is our bar cross section. Okay, bar cross section. But in our case, we from the area we selected the rectangular kinds of cross section. Okay, don't confuse with that. Actually the problem here is with the cylindrical shape. Now in this case, because I'm simply going to demonstrate the example now, let me assume as this rectangular cross section. Okay, now let me show the deformed shape. Okay, so here deformed shape only, deformed class and deformed. Check the second one. Okay, now when you see here, the first one is the original one, the second one is the deformed one. Okay, we showed the deformed shape. Okay, now if we need to save this this image, this result as image, we go to plot. I think this one's in black background, so this is not printable, because when you print in PDF form, this black background can finish the color from the printer. So we have to go to the plot control, then style. From style, I think then color. From color, reverse video. Okay, when you click this one, the background will be changed to white. Now it is changed to white. Okay, a little bit zoom out. Okay, because it is coincide with the result. Now let me go to plot control, then after here capture image. We're going to capture the image, capture image. Okay, now it is possible to save this result, this deformed shape, to some directory. Go there. Okay, save as. Then you may save any place that you need. For example, in my case, before I saved in deformed and undeformed shape. Okay, the picture looks like this one. Okay, cancel this one, cancel the image. Then go to counterplot. From counterplot, we're going to solve the nodal solution. That one is the displacement. Okay, click this one. Nodal solution. From nodal solution, you have to select the first solution. That one is the displacement. Click along the x component. Then okay. So the results for the displacement looks like this. Okay, when we see the result, it is 0.273 e the power of 3. This one is the displacement. Then when we come to the displacement solution, this one is 2.73 times 10 raised to minus 4. This one is U2. Okay, that one's what? That one's the displacement at node 2. So it is the same result with the analytical calculation. Now we finished for the displacement. Then let me go to the nodal result. That means that is the boundary condition is the force. Go to the nodal calculation. I think it is not here, because in the force case we have to go to the list of results. In the reaction force case, we have to go to the list of results. Then after nodal, that is reaction solution. From that one, select all. Select OK. This is the result for the reaction force. Let me see. Okay. The following XYZ solution are in the global coordinate system. So node 1 and f of x, because we are analyzing under x-axis, so that one is minus 1500. Okay, so it is possible to save this one too. Save as, then you can save any place that you like. Okay, you cancel this one. The value is what? Minus 1500. When we see the analytical solution, the solution is what? Is minus 1500 Newton. Okay, it's the same. Then we finished for the reaction forces, because the second equation is the reaction forces. Okay, the last one is the elemental stress. Let me go for that. Then plot results. Go to plot results. Then after element solution. From that one, select the stress along x-axis. Then OK. Now it looks like this, because the stress in this element is uniform. Okay, because we're analyzing this bar element as single element. So in that case, the elemental stress is 0.191. Okay, 0.191 megapascal. Then we go to the analytical solution, which is what? The stress along x-axis for the element 1. So for the first element is 0.1911 megapascal. Here also it is the same. Okay, now the same applies. If we need to save this stress result, we go to plot control. Then after capture image, then after file saving images that we need. Okay, we finished. Now this one is actually in a plot result. How about if we need the result in list in some node? So in that case, minimize this plot result. Go to the list results. Then after nodal solution, license meta, and come to the nodal solution. We have the result for the displacement. Then okay. Now here the displacement at node 1 is 0.0. The displacement at node 2 is 0.2729. Okay, here at node 1 is 0. At node 2 is 0.2273 times 10 raised to minus 3. It is the same. It is the same. Okay. If you need, can save this one too. Cancel. This we finished for the nodal solution at this displacement. Now, when we come to the element solution, go there. Then click stress. Then after x components of stress. Then okay. Here the same applies. Okay. We do have two nodes. Okay, node 1 and node 2. The stress is the same, because the stress in one single element is the same at each node. Okay, at both nodes. Okay, here node 1 and node 2 is the same, that is 0.191 magnitude. The same applies here to save. Okay, now this is all about the how we analyze bar element in Ansys Mechanical APDL. Okay, Okay, thank you very much for your time. Okay, bye bye.